Yo, what's up? What is up? Friday night, and we're doing algorithms. Okay, we got all the algorithms, we got all the data structures, we got graphs, we got trees, we got linked lists, we got every kind of array you could possibly imagine. Well, maybe not every kind of array, but one of these days we'll have every kind of array you could possibly imagine. Uh, Today, I wanted to take you through a little more involved problem. It's a LeetCode medium problem. And Before I continue, if you like this video, like, subscribe, and don't forget to comment below. Every little bit of interaction you provide me helps me be encouraged to make more videos. And one day I probably expand what I'm doing into a more helpful learning session for all y'all guys and people. Okay. So anyway, this is LeetCode problem 1557, minimum number of vertices to reach all nodes. So I haven't done a graph problem yet, other than your typical tree problem, which a tree is a graph. But this is one of your more not. This is a non-tree graph. Okay, the first non-tree graph problem I've done. It's a DAG problem, right? So given a directed acyclic graph with, and by the way, a lot of people have a problem at saying directed acyclic graph. A lot of people say acyclic. Okay, it's acyclic, and it's acyclic because the graph contains no cycles. Like, I even know of a person at Google who is actually a pretty high-ranking person who calls it an acyclic graph. Okay, that's an anecdote, but believe me, I've heard it before. Okay, places you wouldn't expect. Anyway, given a directed acyclic graph, a DAG, with n vertices numbered from 0 to n minus 1, and an array edges where edges of I equals from 2 represents a directed edge from node from I to node to I. Okay, that's just a standard graph definition. Find the smallest set of vertices from which all nodes in the graph are reachable. It's guaranteed that a unique solution exists. Notice that you can return the vertices in any order. All right, so basically what it's saying, what it's asking you to do, and by the way, the input is an edge list, so graphs typically have, graph problems typically have inputs that are of one of three forms: an edge list, adjacency list, or an adjacency matrix. I personally like adjacency lists because they're pretty easy to traverse, and adjacency matrices are also pretty easy to use. Even though they're larger, they're pretty easy to access, but they typically have a lot of empty space in them. So the space constraints of a adjacency matrix representation, there's a lot of places where there's no nodes. So you have a lot of empty space, right? It's like typically, in many cases, a sparse matrix. And edge lists, I'm not a huge fan of, and I think most problems don't try to give you input in the form of an edge list, but this is what it is. And so these are the edges. So you have an edge from 0 to 1, from 0 to 2, from 2 to 5, from 4 to 2, right, which is this edge, and from 3 to 4. So basically, the minimum number of edges that you need, the nodes that you need to you start at in order to traverse the graph. So basically, this is interesting because you would think that this is some sort of combinatorial graph problem, right? Graph traversal problem. I mean, to traverse an edge list, you could do a DFS, right? But here's the tricky part, right? You have to know the minimum number of start nodes, right, that you need. So you have a start node at 0, start node at 3, and then so how would you do this? Like, for this problem it would be easy, but what if you have a problem that has like a bunch of different nodes in a very large graph, right? It might not be easy to know what the minimum set is that you need to traverse the entire graph unless you do combinatorially traverse the entire graph through doing recursive traversals, right? So you could do it 0. Can you traverse the entire graph with 0? No, you can only traverse this part of the graph and this part of the graph, so 0 to 1, 0 to 2 to 5. And with 3, can you traverse the graph? Yes, but only this part from 3, 4 to 5. So, but these two start node traversals would cover the entire graph. Okay, but sometimes would it be 3? would it be 5? Again, you can imagine that this problem could get complex. Luckily, there's a little bit of a trick here in this specific problem, in that if you think about it, you don't need to actually traverse these nodes, okay? Because what is the minimum set of nodes? Well, think about it. The minimum set of nodes is always going to be every single start node, right? And think about it, because how can I traverse a start node without starting at it, right? It would have to be, both of these would have to be in the set, okay? I could, at a minimum, I have to have both of these guys. At a minimum, I have to have in this 1, 2, 3. I have to have the 3 start nodes. And you know what a start node is, right? Because it's a node that has no in degree going into it, into the vertex. So that means that essentially the algorithm that we could use is that look for all nodes that have out degrees, and just add those to the list and call them the minimum, because you could never get to this node unless you started at it, right? There's no in arrow from anywhere else. So that actually is interesting. Then that's probably a lemma or a theorem of some kind, right? The minimum number of nodes to traverse a graph is, and this is also a connected graph, remember, is the number of nodes with 0 in degree. Okay, and in degree again is the number of number of arrows going into the graph. So if this node here has an in degree of 2 and an out degree of 1, this node has an in degree of 1 and an out degree of 1, and this node has an in degree of 1 and an out degree of 0. Okay, so let's start. So first, what I would like to do is I wanted to create a list. Integer result equals new array list, because I'm going to be storing my result in an array list, right? And the result is just going to be all the nodes. Now, here's where the tricky part starts. We're going to want to start at we're going to record the nodes that are non-start nodes, and I'll explain in a second why I want to look at non-start nodes. Equals new boolean, and a new boolean and is the number of the vertices, and also the labeling of the vertices. And so the nice thing about having a boolean array like this, by default it starts at n. It starts at all of the indices are false by default. So what I can do is, for int I equals 0, I less than edges dot size I plus plus, okay, non-start nodes edges dot get I get 1 equals true. Okay, what is this saying? What is this loop doing? This loop is going through the list of nodes, right? And it's basically getting any node that has an out degree, right? That essentially, if you look at what is edges get I of 1, that's the second for each sublist here, which each sublist represents a node. That's the second vertex, or the destination vertex of each node. So if the destination vertex is in, if there is a number that's in this destination vertex for any of these edges, then we know that that node is a non-start node, right? So for example, 1 is a non-start node, 2 is a non-start node, 5 is a non-start node, and 2 happens to also be an in node, but it's also a destination node as well. The only nodes that are not present as destination nodes, right, would be 0, because 0 is not get edges of 1, is not the second element of any of these, and 3 is not the second element of any of these edges. So both of those are non-start nodes, and what that means is that we are going to mark them, right? And so at that point, for int I equals 0, once we have all the non-start nodes, I less than non start nodes.length I plus plus if not non-start nodes I result dot add I. Okay, so basically, if we find a non-start node, return result. If we find any non-start node that we find, if we iterate through this list and find it's not a non-start node, or this is going to be false here as a start node, then we just add it to the list, and that satisfies our original condition that we were talking about, that the minimum number of nodes needed to traverse the graph that you need to start at is pretty much all the start nodes. Okay, any not a non-start node would be a start node, and therefore adding it to the list and return the list of start nodes. So let's see if this works. Okay. Cannot find symbol. Ooh, shred that. I'm gonna go to the little bitty riggers. Okay, accepted the output, and let's try submitting it. Bam! Look at that, 96.61%. Pretty good. Memory usage 78.8 megs, less than 96.14% of total. So I'm the 92nd percentile in terms of speed and 96th percentile in terms of space. This is an O of n algorithm in terms of time and space, right? O of n being the number of vertices, okay? Because I'm just storing the number of nodes, and I'm iterating through the number of nodes, and then returning that as a result, being the maximum as n all nodes. So that's it. This is a medium problem again. If you have any questions, leave them in the comments below. Otherwise, I'll have a good night, and I'll see you tomorrow.